Hi, my name is Nolasco and I'm a PhD candidate at the University of Michigan in the Rehabilitation Biomechanics Lab. We perform many turns throughout our daily lives, and those turning steps make up between 35 and 45% of our daily steps. However, those turning steps are biomechanically different than walking in a straight line. For example, when we turn around a corner using a step turn, we begin reorienting our body to a new direction with the leg on the inside of the turn supporting our body weight, but also generating forces to accelerate the body center of mass toward the turn. Then, the subsequent contralateral step results in a large ground reaction impulse to push our body towards the turn. The differences in roles between the leg on the inside and outside of a turn likely make turning more challenging than walking in a straight line. This is especially important as there is greater risk of slipping and falling during turning compared to walking in a straight line. As the force modulation used during turning primarily comes from the ankle joint muscles, active ankle control is important to maintaining dynamic balance during a turn. One group where turning may be more challenging is people with a transtibial amputation, as they do not have neuromuscular ankle control. This affects their ability to generate forces for body support and balance control. Thus, people with an amputation have a greater risk of losing balance compared to people without amputation. One way to measure dynamic balance is whole body angular momentum, where a greater magnitude of angular momentum away from zero indicates an increased risk of losing balance. Specifically, people with an amputation have greater ranges of whole body angular momentum during straight line walking, suggesting a greater risk of losing balance. And since turning requires greater balance control than straight line walking, the risk of losing balance may be greater during turning. Thus, the purpose of our study was twofold. One, to determine the influence of turn direction on whole body angular momentum during 90-degree turns in people with amputation. And two, to quantify the differences in whole body angular momentum during 90-degree turns between people with and without amputation. We collected full body kinematics for 8 people with and 8 people without amputation as they made right and left 90-degree turns. As you can see in the video, for people with amputation, this meant that the prosthesis was either on the inside or outside of a turn. We built a 13-segment model in Visual 3D and adjusted the inertial properties for the prostheses to calculate angular momentum about the center of mass for each segment, and then added each segment's angular momentum together to get whole body angular momentum. Lastly, we broke up the turn into different strides, which included the initiation, continuation, and termination strides. The initiation stride was the first inside leg stride. The continuation stride was the subsequent contralateral stride taken with the outside leg. And the termination stride was the last inside leg stride, which completed the turn. For each stride, we compared range of whole body angular momentum between turning with the prostheses inside and outside of a turn, as well as between people with and without amputation. While we made all comparisons and analyzed all 3 planes of motion, I will focus on the frontal plane as it is most relevant for balance during turning, and I will focus on the comparisons for people with an amputation turning with the prostheses on the inside and outside of a turn. Looking at the average whole body angular momentum across the entire turn, we can see that there are greater peaks when turning with the prostheses on the inside of a turn compared to turning with the prostheses on the outside of a turn for each stride of a 90-degree turn. Taking the peaks in every stride allows us to measure the range of whole body angular momentum, and as you would expect from looking at the trajectories over time shown here on the left, we see a significantly greater range of whole body angular momentum when turning with the prostheses on the inside of a turn compared to having the prostheses on the outside of a turn within each turning stride shown here on the right. Thus, our findings suggest that turning with the prostheses on the inside of a turn has a greater risk for loss of balance compared to turning with prostheses on the outside of a turn. This is likely due to the lack of force modulation available on the inside leg when the prosthesis is on the inside of a turn. While different prosthesis components or properties may have an effect, gait training may be useful for improving overall balance control. Therefore, future work should explore if including additional practice performing turns with prostheses on the inside of a turn during gait training for people with a transtibial amputation can improve functional mobility and reduce the risk of losing balance. Thank you to everyone who helped with the study, and thank you for listening. And if you thought to yourself, well, how do segments contribute to whole body angular momentum? Then check out my poster in the Balance and Falls general poster session at the virtual ASB 2020 conference or on the Rehabilitation Biomechanics Lab website. Thanks again.